Hello, my name is Zachary Dougherty from the University of San Francisco's Masters in Data Science program, and today I'm going to be talking to you all about why employees leave. So, in the business world, employees leaving a company is known as attrition, and this can happen for any number of reasons, such as an employee retiring, moving on to a different company, or even getting fired. So, it's important for a business to understand the primary attributes which can lead to attrition so that they can prevent it in the future and reduce their turnover rates. So, the primary goals for this project are one, to predict employee attrition, and two, to discover the factors that can lead to attrition in the first place. So the data used for this project comes from Kaggle.com, and it comes with about 1,200 observations and 30 features, which are a mix of demographic and socioeconomic features, such as the age of the employee, how long they've been at their current company, what their job level is, even their education level. So we have a lot of information about these employees to determine what is the biggest play into why they might leave a company. We also have a target column, which is a binary indicator for attrition. Now, the biggest problem that I had in dealing with this data set is that there's a large class imbalance. So, in fact, 84% of the observations in the training data set were from non-attrition employees, while 16% were from attrition employees. So, based off of this, we need to create our model architecture in such a way that it can deal with this class imbalance. With this class imbalance and the goals of our project or the business outcome in mind, the goals will be to optimize for a high recall. Now, what this essentially means in business terms is that we're going to be over-predicting attrition of employees, which will lead to a low precision. But this isn't necessarily a bad thing, because what it will consequently do is have more employees labeled as attrition than there actually are, and maybe even some who aren't at risk, but it will allow us to check in on a wide range of employees so that we guarantee or ensure that we miss the fewest amount of employees who are at risk. With this in mind, I trained a few baseline classifiers with this hard-coded class weight in mind, and we got these results. So based off of a few models, we found the linear classifiers such as ridge regression and logistic regression to perform the best on the raw data set with the highest recall of about 77%. We still want about a fairly high specificity, because combination of high recall and specificity will demonstrate like a high separability of our model in regards to the target variable. So with this in mind, I decided to go for a first round of feature engineering. Now, the primary thing I would like to point out here is a technique called discretization. Essentially what this does is take a numeric column, such as distance from home, which we have here, which represents the distance in miles that an employee's workplace is from their home. And essentially what we're going to do is look at the three almost uniform distributions that are present in this histogram. So we have the light color, which represents really close to home, the mid tan color, which represents employees that are mid-distance from their work, and the dark color represents employees far from the work. So essentially, discretization takes this numeric column and changes every value to a category based off of where it is in the distribution, which essentially simplifies the model and converts numeric to categorical variables. This, in combination with standard Z normalization and one-hot encoding, produced the following results. And surprisingly, we actually got reduced performance for our recall metric, which tells me that this type of feature engineering may not be best for this type of model. So let's proceed to a second round. In this case, I decided to not do any discretization and simply do quantile transformations on all of my numeric variables. What this means is essentially I have a histogram of a numeric variable, such as an employee's monthly income, which we can see from this histogram on the top is very right skewed. Linear models do better when their input continuous features are normally distributed. So we can use a quantile transformer from the scikit-learn's API to essentially coerce this distribution to be a zero-centered standard normal distribution, as we can see from the bottom histogram. So I apply this transformation technique to all my numeric columns, again doing a standard Z normalization and a one-hot encoding on the rest of my variables, and I came up with these results, which we're still higher than the first round of feature engineering, but underperforming with respect to the baseline models. What this tells us is a really interesting thing is that while more feature engineering could have been performed, the raw data seems to give the best performance out of all the different feature engineering techniques that we tried. And the biggest increase in performance was adjusting the class weight balance. So with this in mind, I decided to use a final model of a ridge classifier. I found the alpha and solver values based off a randomized cross-validation search of different hyperparameter subsets. So Based off of that, I got best performance according to recall with alpha level equals 10, which is the regularization strength of the ridge penalty, and a solver of SVD. This class weight hyperparameter I'm going to talk in more detail about in the next slide. So what I decided to do to find the optimal class weight was to plot the different metrics which with varying threshold values for the class weight for our minority class, which is attrition. As we can see here, the higher weight we place on this minority class, the better recall we get, which makes sense because we're going to be predicting more of the minority samples correctly as we increase the weight that those samples have. With that being said, our precision decreases a lot, which again is not too important based off of our business goals, but the specificity also decreases with the negative log decay, which is good for us because that means with our fairly high class weight and fairly high recall, we can still get a decent specificity score. So based off of this, I decided to go with this dotted line you can see is a class weight for the minority class, which is about 90%. And with those class weights in mind and the hyperparameters I chose, we ended up getting this performance on the test data. So we get about 84% recall, 64% specificity, and 32% precision, which again, precision is not the most important metric, but still a good idea to see how your model is performing with a variety of metrics to get a more overview of the model. With this being said, let's take a look at the coefficients of our ridge regression model. So interestingly, we can see that whether or not an employee works overtime is actually the biggest indicator into whether or not they are going to leave a company or not. Some of the other very important ones are low job involvement and also employees who travel a lot for work. So with these future coefficients in mind and the metrics from our final model, I like to leave you with this. Number one, don't overwork your employees. Number two, encourage managers to invest in their employees. And third, use more digital communication to prevent employees from having to unnecessarily travel. Thank you so much, and I hope this can improve you and your employees' lives.